Welcome, my friends, to another video exclusive. So I wanted to quickly just talk about taking derivatives of these piecewise functions that we see over here. Now, I think the biggest thing to hit on is, well, whenever we take derivatives of piecewise functions, essentially what we're looking at is this. Well, we want to figure out, obviously, first of all, we want to make sure that there's no jump like this, right? We want to make sure that our function exists, it's continuous in order for us to take this derivative here, right? We don't want no jumps or holes. But the very first thing to do is, well, if I want to take the derivative, well, I'll just take the derivative of the top equation and I get 4. And I take the derivative of the bottom equation and I get negative 2x. Cool. And it says take the derivative of f prime of 4. So I'll go ahead and plug in 4 where I'm able to plug in 4. And if I do that, I get negative 2 times 4. Cool. Well, you'll notice over here, right, we got 4, and over here we get negative 8. Well, we get different slopes from the left and from the right. That means we have a positive slope coming in from the left, right? This is positive slope, and coming in from the right, we have negative slope, right? It's not possible to have different slopes at the same exact point. So we can immediately conclude this is non-existent. Really, you just take the derivative of the top and the bottom, and you better have matching slopes. All right, so let's go ahead and take a look at maybe another problem here. Cool. So here's the function. We want to find f prime of 4. So I'll do the same thing. I'll take the derivative of the top, which is 4, and I'll take the derivative of the bottom, which happens to be 4x. Okay. Now what do? Well, I plug in 4, and if I plug in 4, I'll get 16. Right, and this is 4. Again, slopes don't match. Boom, non-existent. Okay. Let's say though, hypothetically, let's say that in this scenario, let's say we had this right here. Okay, just to show you, let's say we had 4x plus 2, and we have x is less than 4, and let's say we had 4x plus 5. Cool, and we have x is greater than or equal to 4. Well, if I take the derivative of these, okay, I'm going to get 4 and 4. Notice how the slopes match, right? And so you think, okay, cool. Well, now that I know that the slopes match, well, that means that f prime of 4 has to equal 4, right? Because I can't plug in 4, I just get 4 as an output. Well, you still have to be careful, because in order, when you take the derivative, the easy way is just to check to make sure that the slopes are the same, but you still don't want a hole, right? Because you can have a function like this, and they have the exact same slopes, but we know we can't take the derivative here because there is a hole, right? From the left and from the right, there's a jump. And really what we want to do next is plug in the 4 into here. 4 times 4 is 16 plus 2 is 18. And then if we take the 4 and plug it into here, we get 16 plus 5, 16, 17, 18, 19, 20. So we get 21, right? And so I know right away, boom, we have a jump. This is also not going to be able to get the derivative taken care of. So those are two ways to check. Are the slopes the same? And last but not least, are the points equal to each other? So that leads us to this problem over here. Let f be the function given above. Which of the following statements are true about f? The limit as x approaches 4 exists. Well, notice it doesn't have the plus or the minus, so we have to take into the count left and the right. Well, the limit as we approach it from the left of this function is, well, this is x is less than, so I know that's from the left. And if I plug in, it looks like 4 is the number I'm interested in, so 4 plus 3 is 7. Cool, so we get 7 over here. And if I plug in 4 to the limit as we approach it from the right, so the limit as x approaches 4 from the right, we get 12. 3 times 4, which is 12, minus 5, which is 7. Cool. So we now know the limit from the left and from the right does exist. So we know this is to be true. Okay. And if the limit from the left and from the right exists, okay, well, now it wants to tell us if f is continuous. Well, we need, remember, 3 things to be true. For the limit to exist, of 4 to exist, which it does. We already figured that out. And we need the point to be true. Well, if I plug in f of 4, I'm just plugging this into the top equation, which will give me 7. Cool. And condition 3 states that they need to be equal to each other, which they are. So I can conclude that this is true. So we know the limit exists and f is continuous. Now we're asking ourselves, is f differentiable at x is equal to 4? Well, can we take the derivative too? Well, if I go to actually take the derivative, cool, all I do is just take the derivative of the top and the bottom, and I get 1 here, and over here I get 3. Well, I can immediately conclude that these have different slopes. You can't take the derivative of a function at a certain point and have different slopes, because remember, to take the derivative, that means we need to have instant slopes. So how could you have two different instant slopes at the same location? So I can conclude this is false. So now I know, well, which of the following statements are true? Well, that's going to be 1 and 2. And that's it, right? And I'm able to conclude from there. Cool. Let's take a look at this next one here. Well, look at this piecewise function. We want to know if f has a limit, if f is continuous, and if f is differentiable. Well, the first thing I want to do is maybe clean up the top. I can factor the top and the bottom like such, and I get x plus 3, right? So I might go ahead and rewrite this to be f of x is equal to boom boom boom, and we get this, and x is equal to 3. And again, if I was to graph this, I know this is going to look something like this, where you have a hole and something and some filled in circle, and we're trying to see if this fills in or not. So does f have a limit? Well, of course it's going to have a limit, right? Because this is, if we think about this, well, the top equation says we're not able to equal 3, but that does mean we can be equal to any other number. So we know as we approach it from the left and from the right, even though we can't equal 3, it will approach some y value. In this case, if you actually plug it in, we get 6, right? So we're actually approaching 6. So we know this is to be true. Well, is f continuous? Well, the limit is true. Well, does the point exist? Well, f of 3 is 2. Well, the limit as x approaches 3, we just literally talked about this, is 6. Since they are not equal to each other, we know it's not continuous. That is false. Good. And then the last thing to do is, well, we need to take the derivative. Okay, and if I take the derivative, well, the derivative of this right here, which is being simplified, is 1, right? And down below was a derivative of 2, we get 0. Obviously, the slopes do not match up. So I can officially conclude that this is not differentiable. So the only thing that is a true statement is A, all right? Because it only has a limit. It's not continuous because we have a hole. We have this non-removable discontinuity. And last but not least, we are not differentiable. Well, why? Well, because when we take the derivative, we get different slopes at those points. All right. Well, I hope you have yourself a wonderful day. And that was it, literally, for the 5% bonus.